Welcome everyone to today's colloquium. It's my pleasure to introduce Heather Macbeth from Fordham University. Heather got her PhD from Princeton under the supervision of Gang Tian, where she worked in color geometry. She then had some postdoctoral experience all over the world. She was at MIT in the École Normale Supérieure after this, she joined Fordham University in 2019. So it's now my pleasure to introduce Heather, who is gonna speak about formalizing, making mathematics computer-checkable.
Hi, thank you. It's a pleasure to be in Montreal, virtually at least, and to see some faces that I know and some names that I've heard of before. So as you've been told, I was trained as a differential geometer, and it's been a subject I've loved, but in the last couple of years, I've become interested by another part of mathematics. And this is the field of formal proof. So the field of really being able to make real the promise that I think we've all had, for thousands of years, of being able to make mathematics really work down to the axioms. I think that this is something that we all value and that perhaps is increasingly in sight. So the technology that permits this is called the technology of proof assistance or formal verification. And I want to indicate briefly what I mean. So an interactive theorem prover is a system in which you have a mental aid for keeping track of how your proof is going. You have a display like this, which consists of the variables that you currently are keeping track of, and the hypotheses that you currently know, and the goals that you want to prove. So in this little picture, I've got a function from the natural numbers to the integers, so a sequence, and I've got a hypothesis, which has got a universal quantifier. So it's a recurrence relation that for all n, fn plus 2 is fn plus 1 plus fn. So this is the Fibonacci sequence. And I've got another natural number on the go. This is my index n. And I've also got indicated by this turnstile signal here. You can see my cursor, yes. I've got indicated by this turnstile signal here, symbol here, a goal, and the goal is to prove one of these standard identities about the Fibonacci sequence. You might note that I actually didn't give you enough information because I didn't tell you how the Fibonacci sequence was supposed to start. So I mean, this is a toy example for various reasons, but this is I think a reasonable model to what we all have in mind when we try to prove something. We have certain things that are our variables, certain facts that we know, and certain facts that we're trying to prove. And an interactive theorem prover is a system that manipulates objects like this called a goal state, and moves you from one goal state to another goal state to another goal state by means of a programming language which lets you give instructions, and each instruction you give is a valid mathematical deduction that turns you from one set of hypotheses and goal into the next by perhaps applying a known theorem to modify the goal to some other kind of goal, or perhaps to deduce something from one of the hypotheses you have, or any number of other things. This is a technology that has been around for a while, and I wanted to mention, I guess, a couple of highlights of the field over the last 30 years. There are several programming languages, Clock, Isabelle, and Hall Light, and I guess I should mention Mizar too, which have been around since the 80s or 90s. And they have had a lot of achievements in really large scale proofs. I mean, proofs that are sort of so large that I think most mathematicians certainly acknowledge that it would be very hard for a human to keep all the ideas in their head. So the three big ones that I'd like to mention are a proof of the Four-Colour Theorem, a proof of the Odd Order Theorem, and a proof of the Kepler Conjecture. And the first of these was produced by Gontier, the second by Gontier and a team, and the third by Hales and a team. Interestingly, both the first and the last of these are proofs which are sort of beyond the reach of human comprehension, because as originally published without a formal proof, they contained very large computer computations. And so part of what you would want in a formal proof of them is a proof that, when you send, your MATLAB or your Mathematica or your Sage or whatever out to carry out those calculations, that it's really computing what you think it's computing and not something else. So that's a very reasonable thing that I think we would all worry about when we saw a standard proof that was partly computer code. The proof in the middle is not like that. As far as I know, the work on the classification of finite simple groups did not feature any large-scale computations in a computational algebra package. But it's somehow similar in spirit in that it's a relatively restricted domain, and it's this. I mean, to the extent that I know much about this proof, I understand that it's, somehow a finite number of techniques being used repeatedly, and somehow the experts got to know, I believe, sort of the mechanical steps that you would use to perform out those steps. I mean, again, this is not my expertise, and I apologize if I'm underselling it. But that's clearly not the end of the story. I mean, it seems that one would hope not just to formalize results of this kind, but any kinds of mathematics. And I think that this promise is in reach. So I want to first demonstrate a new theorem prover, the lean theorem prover, which has been only around since 2014, and maybe briefly demonstrate to you what it's like to use it. And then I want to touch on some successes that this has had in the last couple of years in improving, really, research level mathematics. And finally, for the last part of the talk, I want to try to explain what it feels like to work in a theorem prover, not just at the sort of toy level that I'll be modeling in the demo to come, but at the level of working with the mathematical objects that we encounter in grad school. So let me now switch to sharing my screen to some computer code. So I should now, I hope, have visible for all of you a screen which has two parts. The part on the left is the part where you write the computer code, and the part on the right is the part where you see the goal state that I was previously describing. So you can make definitions in this language, and I've defined a limit of a function from the natural numbers to the real numbers, which is therefore a sequence, and a real number L to be the predicate that for all epsilon greater than 0, there exists a natural number n, such that for all little n greater than or equal to capital N, the absolute value of the nth term of the sequence minus the limit L is less than epsilon. So this is our standard definition of limit. And I want to prove for us the theorem that if you have sequences A and B, which have limit L and N respectively, then their sum has the limit L plus N. So if I now click inside this begin end environment, I've written the word sorry, which I can comment out. And you see on the right of the screen, I've got the kind of goal state I was describing at the start of the talk. I have my two sequences A and B from the natural numbers to the reals. I have the two real numbers L and N, and the hypotheses HA and HB, that A has limit L and B has limit N. And I've got my goal that the limit of A plus B is L plus N. And so I'm going to prove maybe not all of this, but enough to give you the sense. I can start by telling it to unfold the definition of limit. And this now, as you can see, as I move my cursor from one line to the next, it transformed the goal state according to the instruction given at that line. So it's transformed the goal state here to the version in which the hypotheses and the goals have been replaced by their formal definitions. So now I see the hypotheses and the conclusions all expressed in terms of epsilons. Okay, so what would I do? I would say, let me take a particular epsilon and I'm going to prove the result for that particular epsilon. And so I type a command which moves me from a universal quantifier for all epsilon in the goal and a hypothesis that epsilon is greater than 0 to a goal state in which I've got that epsilon and that epsilon greater than 0 ready to work with under the name epsilon and h epsilon. And then what would I do? Well, I guess the standard proof would be that I consider epsilon over 2 for each of the 2 sequences that are being summed. So I want to apply my hypotheses HA and HB in each case with epsilon over 2. I should probably first establish that epsilon over 2 is also positive. So this now sets me up with 2 goals. I have an intermediate goal of establishing that epsilon over 2 is positive. And then once I prove that, I will still be back to my original goal of proving, what I wanted to prove before, but I'll have to aid me this extra fact that epsilon over 2 is positive. And at this point, I can invoke one of the small computer subroutines to establish facts. This is a fact that establishes inequalities, linearith, and it sort of chases around any inequalities that are available in the known hypotheses and concludes things that are trivial arithmetic modifications of that. So now I know that epsilon over 2 is positive. Next, I want to apply this fact to my HA. So I'm going to make a new fact, capital HA, let's call it, which is the result of applying HA to my epsilon over 2. This h epsilon that I just established. And now you'll see that I have a new hypothesis, which has been added to the goal state because I obtained it by a valid deduction, namely specializing the previous hypothesis that there exists a capital N such that every little n past that satisfies the epsilon over 2 desired. And I can do the same thing for the other sequence. And okay, now I probably want to extract the capital N associated to each of these 2 sequences, the point at which things start to work. So I'll use a tactic called cases. And this gives me, out of an existential, the existence of the capital N, that turns that into an actual variable N1 available in my goal state. And the hypothesis saying that past that, the sequence has the behavior I want. At this stage, I have my N1 and N2, and what do? You say, let's take the maximum of those 2. So I'll use the max of N1 and N2. And this has now changed my goal, which was an existential, the existence of an N such that everything past a point worked, to the goal of proving it for that particular capital N. And now I've got a universal quantifier in the goal again, so I might want to introduce a particular natural number N, which is past that point, and the hypothesis that it's past that point. And okay, well, one fact that I'll probably want to know is that this N is greater than or equal to N1 so that I can apply this hypothesis to it. So I'll state the fact that N is greater than or equal to N capital 1, and this should follow from the fact that it's greater than or equal to the maximum of N1 and N2. In this case, this isn't something I can call the proof finding routine linearith for, because it's not somehow an arithmetic calculation. Instead, it's a very small theorem about the maximum. But I can search the library for this. And this is quite a powerful tool that modern theorem provers have. You can search the library of all previous things that have been proved and find the lemma which states the thing that you want, that that if a number is greater than or equal to the maximum, it's greater than or equal to the thing on the left. I think I don't want to go through to the end of the proof, but I hopefully have convinced you that you can carry out any of the sort of natural logical steps that you would want to, you know, by the appropriate manipulation of the tactic state. I'd be happy actually to pause at this point if anyone has questions about the sort of interaction that I've just demonstrated here.
Are we to believe a library is perfect, that all the things it claims to know are true?
That's a great question. You can download the library yourself, and you can compile it yourself on your own computer. It'll take about 4 hours to build. And at that point, you know, the correctness of the library is reduced to whether or not you believe that the software compiler that was used to check all the proofs in the library. So I guess it reduces it, you know, from checking the entire library to checking the rather smaller piece of software that verifies the library.
I can also download MathSciNet.
What was that?
I can also download MathSciNet.
You can also download MathSciNet, yes. Do you trust everything in MathSciNet?
No, but I'm trying to make the analogy that they're roughly the same level of belief, optimistically.
Yeah, I don't know. I think, honestly, I believe this more than MathSciNet, at least in the aggregate. But I mean, there have been notorious cases when, you know, at least temporarily, a version of a popular theorem proving software has had a logical inconsistency in it. And that's obviously something that you don't want to last for long. I'm going to jump back to my slides at this point. So a very notable recent achievement of theorem proving software has been a proof of a result of Peter Scholze. This was a result that Scholze himself was, I wouldn't say perhaps necessarily uncertain, well, maybe uncertain about it is fair. At least felt perhaps he had not found a human referee who sort of had the energy to go into all of the details. And he reached out to the community of people working with this lean theorem prover, and indeed with all of the other theorem provers, to see if there was anyone interested in taking on the challenge of verifying this theorem. So it's a theorem on some level about analysis, about working with collections of objects and sequences in normed spaces, but on a somewhat algebraic level. And this succeeded. So about a year ago, Scholze was able to announce that the team of people who had been working on this challenge that he had posed had succeeded in proving it. So at least now, in principle, it's possible to verify results at the research frontier, with a few caveats. So you need a fairly self-contained target result, something that, I mean, does not need to be necessarily so concrete. So it doesn't need to be just a statement about groups or polynomials or the real numbers. It can be a statement about norm spaces and you know, and functors, but it still needs to be fairly self-contained, because it can't build on too much in the way of previously developed mathematics. If it depends on 40 years of the developments in your field, it's probably out of reach. But if it depends on 1 or 2 graduate textbooks, it might well be within reach. You need one person who really understands the result and who really is an expert with proof assistant, who is willing to somehow lead the project, at least in the practical experiences we've had with this, and who can divide up the task into many smaller tasks. In this case, this was done by Johan Kommelin, who's a postdoc in Freiburg, and who spent a ton of time, you know, really understanding this proof in detail and identifying tasks that could be farmed out to a large group of other people. And then finally, you need a lot of time, because although, as you can see, you know, the computer can fill in very small steps like that arithmetic calculation from epsilon positive to epsilon over 2 positive. You can't go too far beyond that. You just need time, as things are at the moment. And so you either need a medium-sized number of people with a lot of time, or you need a large number of people with a medium-sized amount of time, or possibly a large number of people with a lot of time. I really had the pleasure of contributing, a small number of lemmas to this project, but I was perhaps number 20 down the list of people who stopped by for an afternoon and tossed in a lemma here or there. And I think that this at the moment is how this kind of thing gets done. You have a reduction to a series of puzzles which can be carried out by the people who drop by. So it's at the moment not practicable for all of mathematics, but it is practicable for high-profile pieces of mathematics that can attract a lot of people. I think there's promise in the future for something more wide-ranging. So I want to also mention briefly a really promising recent result in artificial intelligence. So since you can express mathematics in this way, you can send it off to the people that are working on machine learning. And at least when mathematics is expressed in this kind of language, it becomes a target that a computer can understand. So people are working very hard on getting computers to use neural networks and so on to solve the mathematics, at least simple mathematics in these systems. The big recent result by a team at the outfit OpenAI was to be able to prove a series of relatively creative high school problems, Olympiad-style problems. And I've got here a sample of the ones that they report that their system was able to prove automatically. For all integers n greater than or equal to 9, prove that this formula is a perfect square. So you can see there is an idea here, and the idea is coming up with the witness, which, if I remember correctly, is n+1. So it's a little bit impressive already that the computer was able to think of using the witness n+1. It was trained on, I guess, thousands and thousands of other past problems for this kind of thing. And it had an idea for, maybe how complicated the witness would be, and maybe tried a bunch of things and followed its nose a little while with each of those things. So I don't know, I think if the artificial intelligence develops further, we may get to the point where it goes beyond high school puzzles to a reasonable age that will help us in carrying out large formalization tasks. What I want to switch to now is a description of what it feels like now to do mathematics in these systems. I mean, now before the sort of promise of the future with the wonderful world of AI has been realized. So I was inspired by Scholze's description of his feeling about the experiment. He was asked, can you read the lean code? And he said yes and no. So he said, yes, I can read the definitions and theorems. And I think perhaps you can see that from what I wrote before. They're written in terms of quantifiers, and definitions that boil down to quantifiers, and they're relatively accessible to the outsider. On the other hand, the proofs themselves tend to be pretty opaque until you've read thousands of previous such proofs, or perhaps hundreds is the right scale. And I think that for that reason, I want to divide the rest of the talk into two. I want to talk first about the language and how it feels to try to express yourself in the formal languages that we have for doing formal proofs. And then I want to talk about the proofs themselves and what it feels like to come up with those proofs. I want to start by dispelling what I think is a misconception that I often see when I talk to colleagues about this kind of software. So I think it's very natural coming to this kind of software to think that, to have the intuition that you want to make it simple, to explain it to the computer, to make it concrete. You might have an idea in your head and you say to yourself, okay, well, I'm going to really boil it down into a fact about a list of vectors, or a fact about epsilons and deltas. So, here I've got a statement, that for any k vectors in Rn, if k is bigger than n, then I can find these coefficients c1 to ck, which, appropriately paired with all of these, and it gives 0. So that is a translation of, I guess, a fact about linear algebra that can be expressed much more abstractly. Or, it would be tempting, I think, to have a fact about continuous functions and to say, okay, really, well, yes, I can come up with, an explicit function of the following form, sum of ai to e to the power of I, which is smaller in absolute value than epsilon throughout some interval of interest. And the point I want to make is that this is really not necessary with modern theorem proving languages. So you can express it in the language that you would naturally express it to a colleague. You can express the first statement as saying that if you have an n-dimensional vector space over a field and a number of vectors in that vector space which is greater than the dimension, then they're necessarily linearly dependent. You can express the second fact genuinely by constructing an object C01, comma, R, the space of continuous functions from the unit interval into the real numbers. You can put the subnorm topology on it, and you can state that polynomials are dense in this space. So there are no compromises in that sense. You can talk about the objects that you would want to talk about in the way that you want to talk about them. And it really is turtles all the way down. You can make definitions layered on top of other definitions, layered on top of other definitions. Of course, these definitions do boil down to the concrete versions, but you can work with them on the level that you're accustomed to working with them as you write on paper. And in fact, it's easier this way. So the sort of Bourbaki version is usually actively pleasanter to work with than the very concrete version. So I want to spend a little bit of time just giving a sample by mentioning some results, or not even some results, just I think some sentences that you can translate into Lean, the language I know best, perfectly well with the current state of the art as far as writing mathematical libraries is concerned. So those of us who use the proof assistant Lean have a sort of collaborative project, a library called Mathlib hosted on the open source platform GitHub that totals the better part of 1 million lines of computer code, and which covers the better part of the undergraduate curriculum and some of the graduate curriculum. And I've really just taken bits and pieces from the kinds of things that I see people contributing to that library in the last few months, with a bias towards my own training, which is in analysis and geometry, just because that's what I understand better. But I've tried to be representative. So, here's something that I saw Kalle, who is a probabilist in Finland, expressing a few months ago. You can say, let X be a topological space, consider the space of bounded continuous functions from that space into the real numbers. You can make this naturally into a Banach space. That was done by Sebastian Guzel and Ren. You can take its topological dual. You can take, so that's the space of continuous maps from that Banach space into the real numbers. You can put the weak star topology on it. And then you can take the space of probability measures on X, I guess, with respect to the Borel sigma algebra. And you can naturally embed that space of probability measures into the dual of the space of bounded continuous functions and pull back the topology to induce a topology on the probability measures. All of this, goes through just fine. Like, all of these statements, I haven't written the Lean code, but I think I'm not cheating when I say that, all of the words I said really just are definitions in the language Lean that say what you would expect. So let me run through a few other examples. And I want to emphasize that this is really very partial and random and just picking things that I happen to have heard of or know well. So you can say, take a perfect integral domain of characteristic P, take the ring of wit vectors over K that was defined by Johan Kammerman in Freiburg and Rob Lewis at Brown. And you can define an isocrystal over K to be a finite dimensional vector space over the field of fractions of the ring of wit vectors and to group it with a Frobenius and a linear isomorphism. That was actually my own work with Rob a few months ago. I'd like to mention some work by someone in the audience. This is Frédéric Dupuy at the University of Montreal. So you can take two Hilbert spaces E and F. You can take the space of bounded continuous functions from E to F, and also the space of bounded continuous functions, bounded linear maps from E to F and bounded linear maps from F to E, and then make a bounded linear map from the first space of bounded linear maps to the second space of bounded linear maps. That's a construction on top of a construction on top of a construction, but it works just fine. And of course, you want to be able to do that because that's what the adjoint is. So this is joint work by Johan, by Scott Morrison at the ANU in Australia, and by Adam Topaz in Alberta. You can take a topological space, take its singular simplicial set, and take the associated normalized Moore complex, and then take the homology of that. You can take a smooth manifold. This is a very large manifold library, still on the level of just smooth manifolds and smooth maps and simple facts about them, but it takes a lot of infrastructure to build up a manifolds library, and it's been a lot of work. So this was done by Sebastian. And you can do the construction that you would want for the Whitney embedding theorem. So you can take a finite regular covering in a subordinate partition of unity, and then you can construct some associated map by, for each of the charts appearing in the partition of unity, construct a map into one dimension more than the chart in question, and add those together side by side to formulate in the end something that ends up being an embedding of the manifold into Rn for n very large. This was done by Yuri Kudryashev, who's a postdoc in Toronto. I wanted to mention this example about graphs, even though it's not perhaps very showy, because I think it illustrates an interesting point about the language there is. So this was done by Aaron Anderson, a grad student at UCLA. You can say, let G be a graph on the vertex set V, and then take the adjacency matrix of G as a matrix on V cross V. So this illustrates a point which perhaps might initially seem like a drawback of the computer formulation, namely that in Lean, you have to select for a matrix, an index set for each of the dimensions. It's not sort of automatically on the set 1 to n, the way that we might implicitly take it to be when working on paper. So it might seem frustrating to carry around like a random index set in each of the two dimensions for your matrix. But then when you come along to actually using a matrix in context, like in graph theory, it's actually perhaps really nice to not have to say, we select an arbitrary labeling of the vertices of our graph from 1 to n, and then in that order, we write down the adjacency matrix. Instead, you can have the adjacency matrix really living indexed by the vertices of the graph. So I think this is a case in which what might seem like an awkward computer formulation turns out in some ways to be relatively pleasant when you think about it. And then finally, another piece of work of my own. So you can take the unit circle, which is, I guess, a topological group, and therefore by work of Floris van Doorn, a postdoc in Orsay, you can equip it with Haar measure. Then you can consider the Hilbert space of square integrable functions on it, which was constructed by René Desjens at INRIA in France. So this is a Hilbert space under the inner product of integration. Modular agreement almost everywhere. And then you can cook up an orthonormal basis for it. And I guess the point that I want to make here is just that, you have theories interacting with theories. You can make a Hilbert space in some concrete way. In this case, by considering square integral functions on the circle. And then you can apply the abstract theory that you might have proved at some previous point for Hilbert spaces. So you might have a theory of orthonormal bases for Hilbert spaces, which you could then apply in a particular instance. And this is the beginning of the development of Fourier series as functions on the circle. So I really want to emphasize that this is an extremely partial list of the kinds of things that people have been working on. This is a massive collaborative project, with a dozen contributions every day from people all over the world, which excites me every time I think about it. But I guess the point I want to make is that those of us who contribute to this regularly are pretty well convinced that anything that you would want to say in mathematics, you can say with the language we have available. There appear to be no particular restrictions in terms of expressibility. On the other hand, the proofs are a different story. So proving things, even at the best of times, is painful in proof assistance. And I think the best that can be said, and what I want to say perhaps for the last few minutes of my talk, is that sometimes, although the proofs, sometimes the proofs are honestly just painful, and I don't want to dismiss that, but sometimes the proofs are different in a way that feels a little bit instructive and maybe has something to teach us, even in the way that we ordinarily think about proof. So I want to take a deep dive into one proof. This is just a proof about Chebyshev polynomials. So recall that the Chebyshev polynomials are defined by some recurrence relation. So these are polynomials in one variable, t sub n plus 2 of x is 2x t sub n plus 1 of x minus t sub n of x. Again, I forgot to write what the base case of the recurrence is. And there's a multiplication formula for the Chebyshev polynomials for all natural numbers m and k. 2 times this product of Chebyshev polynomials is the average of 2 other Chebyshev polynomials. So if you imagine proving this as a human, you'd prove it by induction. The induction is actually a little bit interesting in that you prove it on m for all k at each stage. So you prove it for m equals 1 for all k, followed by proving it for m equals 2 for all k, and so on. So I've skipped the base case because that's not relevant here. I want to say, suppose now we've got to the point where it's true for m and for m plus 1, we're going to prove it for m plus 2. And I've written what I think is a fair description of how the human proof of this kind of thing would go. So you start with the left-hand side, and you inspect it, and you say to yourself, okay, well, I guess at this stage, maybe I can use my recurrence relation. And then you pick that apart and you try to rearrange your recurrence relation now to look like the inductive hypothesis. So here I've pulled out from my recurrence relation one product of Chebyshev polynomials and another product of Chebyshev polynomials. And then I apply my inductive hypothesis to each of those. So I've replaced this one by using the inductive hypothesis as sum of 2 other Chebyshev polynomials, and this one by a sum of 2 Chebyshev polynomials. And then I'm going to rearrange what I've got here in a form that is applicable to still more forms of the recurrence relation. So I pulled out this term and this term next to each other to get this, which I can replace by 2 sub n plus k plus 1 by the recurrence relation again. And this one here, again, by the recurrence relation. And the point I want to make here is that this is designed to be read by a human being. So even though in some sense this is just a computation, like this is written in a way that is designed to be followable and checkable by a human being. Like probably if you wanted to, you could, as I'm about to do, express it in a way that you could type into MATLAB, but we haven't done that. So I want to compare this with the proof I made of this theorem in Lane a few months ago, which has all of the same information, but presented slightly differently. So in Lane, the part that we were just describing, the sort of, series of equations, replacing one thing by the next thing by the next thing, is easy given the right thing. I just state all of the things I want to know. So I know that I have these 2 uses of the inductive hypothesis and these 3 uses of the recurrence relation. And I tell it, take an appropriate linear combination of these 5 identities, each with the right coefficients, 2x times the first one, minus 1 times the second one, 2 times the third one, minus 1 times the fourth, and minus 1 times the fifth. And if you were to give this proof to a human, they would sort of understandably be annoyed because as a human, you somehow expect the proof to do a bit more handholding for you. I think that you would probably be annoyed to have to verify all of these coefficients yourself if this were given to you as the proof. So this is perhaps, one place in which the formal proof can be quite freeing. Things that we don't necessarily always recognize as pure calculations in our paper proofs actually are, a linear algebra calculation or a Gromner basis calculation or some sort of transitive closure of a bunch of inequalities calculation, if you can find the right way of phrasing it as something that could be checked by an algorithm. And I think there's something quite freeing about potentially learning to extract those algorithmic parts of the proofs we make every day. On the other hand, I want to mention that there are some parts of this proof that are much more painful than you would have to do on paper. So for example, the most annoying part of this proof on the computer is that there's a lot of work to identify that t sub n plus 1 parentheses plus k plus 1 in parentheses is the same as, where is it? T sub m plus k parentheses k plus 2. Like you actually have to really sit down and massage the indices to get lean to identify that this term is the same term as that term by normalizing the indices. And so the proof looks, when you see it in computer code, very, very different in emphasis from a human proof. There's a lot of time spent on things that you would think of as trivial, and very little spent on things that you would think of as having content. And this is not always the case, but I think it can often be the case, and it's sort of interesting. I wanted to make a couple of other remarks about formal proof, for which I was having trouble sort of coming up with good examples on slides. One is that it can be very freeing in a situation where you're working with a complicated object to have the goals kept track of for you. So I think in the example I showed, I sometimes had 2 goals going on at once, but I think it's common in a difficult mathematical proof to have 17 goals going on at once. To take an example that I was doing just the other day, you want to construct that a certain thing is a vector bundle, and so you have a series of things to check that it's a vector bundle. You have to show, that, there exist. You have to say what the trivializations are, and you have to verify that these are each indeed trivializations, and you need to check that the transition functions between the trivializations, are linear and that they're continuous. And maybe you want to check that the topology induced by the trivializations is the same as the original topology on the vector bundle. And so there can be so many small things to check that as a human you can lose track, and obviously the computer never will. It can be quite freeing to not feel the obligation to keep all of the proof in your head at once in that way. It can be quite freeing to have the computer generate for you automatically the 17 things you need to prove, and to skim through them and pick off the ones that look easy, and maybe even realize later on that one that you assumed had been easy was not actually easy, or vice versa. There's a sort of freedom in the management of multiple goals that you would not necessarily experience when working on paper. And one final point is that there can be a style of proof that is quite hard as a human being, which can be better on the computer. And that is the style of proof where you say, okay, that's true trivially, where trivially means by definition. You have to unfold all the definitions in your head, and then unfold the definitions of those things, and then unfold the definitions of those things, and really check to your satisfaction that the 2 things that you're claiming, are tautologically equal, are in fact tautologically equal. This again, I'm borrowing from a comment of Scholze. I mean, again, it's interesting that sometimes the sort of computational algorithm that Lean spends to verify that 2 things are definitionally equal can be quite time consuming. It might take Lean, a couple of seconds, but you really, in some cases, can reduce something. I mean, and for example, the kind of thing that you might do in this context is you want to prove the continuity of a complicated function, and you realize it as the composition of 6 different relatively simple functions, which all put together in the right way to verify that the whole thing is continuous. And the computer will think for a while, and it will verify the composition of all of these bits and pieces is indeed the thing that you claim it is. And so finally, I guess I should be fair and explain some of the kinds of things that I think are notoriously difficult with proof resistance at the moment. So they can be fiddly. I mean, this example of the t sub n plus 1 plus k plus 1 not being obviously the same as the t sub n plus parentheses k plus 2 is just the tip of the iceberg. There can be a lot of manipulation of things that sort of are trivially equal as far as you're concerned, that need massaging before they're equal from the point of view of the computer. There can be side conditions. You want to apply a theorem on continuity, and at some point you take 1 over x, and that produces the side condition that x is not 0. And so this goal that x is not 0 has been created for you. And then you do the same thing over and over again, and all of a sudden you have 6 extremely stupid goals to check, one of which is that x is positive, one of which is that x is not equal to 4, another is that sine of x is between 0 and 2 pi, and verifying these can end up being by far the bulk of the argument. And then in some cases, you can have a feeling that what you're doing is essentially algorithmic, but you can't quite pin down what the algorithm should be. I mean, I think nobody yet has come up with a good algorithm, for example, for really saying what it means to say, this is just a diagram chase. You, I think, can tell a colleague that something is just a diagram chase, but I don't think that anyone has a very good theory of what it means to be just a diagram chase as far as actually giving instructions to a computer is concerned. So I think that there's hope here, but the hope needs to be centered in not just mathematicians adopting this technology, and not even just technically minded mathematicians, but algorithmically minded mathematicians. And I would say that I myself don't think I'm that kind of person. People who are able to identify a train of thought that they carry out commonly and really abstract what goes in that train of thought in a way that is useful for future approaches. I think this is a very particular kind of brain that maybe even among mathematicians we don't have very much of. And I think it would be really nice to see people with that kind of process-minded point of view entering the field and writing interesting automation for common kinds of arguments in their mathematical area. So I think that's all I have to say. I'll leave it there. I wanted to just leave with a few links in case you're interested in learning more. So the group of us of mathematicians who are working on this project of having a single interoperative mathematical library, maintain a blog where every month or so we post an update on what's joined the library in the last month. You can follow discussions, which I think are quite interesting for a lot of outsiders, about the design decisions of, should we define manifolds to be simultaneously over the real and complex numbers, or should we have separate real and complex definitions? Do we want to take a filter-based definition of continuity or a net-based definition of continuity? I mean, and anything in between. This is, I think in these design decisions, we quite often have outsiders stepping by and offering their point of view, and I think this is a strength of the community. You can try out a game written by Kevin Buzzard and Imperial to test out Lean in the very simple case of the piano construction of the natural numbers. And once you're really converted, you can download it to your own computer at the installation instructions I've listed here. At that, I'd like to thank you for your attention and for inviting me to give this talk.
Thank you very much, Heather, for the very nice talk. I think it's now time for questions. So raise your hand if you want to ask something. I see a question by Samuel Desroches, please.
Hello, thank you very much for the talk. It was great. I wanted to ask about when you were talking about how like we have all these definitions about rings and groups and manifolds and everything, but we can eventually unfold everything down to the basics. I was wondering if everything eventually gets unfolded to set theory.
So this is not an area of expertise of mine, but Lean is built on top of dependent type theory. So I'm not a logician. All I know is that it's different from set theory, but yes, that's the logical foundation.
And I just had another follow-up question
Mhm.
about you were talking about the expressiveness of the theory. So are the current Lean libraries able to express things like category theory, which are kind of more
Yes.
not set theoretical?
Yes, so there is a very large category theory library. The first person to develop it was Scott Morrison at the ANU, and since then I think that Adam Topaz in Alberta has really joined him in pushing this forward. It's not an expertise of mine, so I can't say too much, but it's certainly, many, many tens of thousands lines long, and I think it's quite powerful.
Thank you very much.
Okay, I see Andrew has a question.
Yeah, you explained very well about how you can verify a proof with Lean, but as mathematicians, we look for insight from a proof. So how is Lean going to help us with gaining insight?
So that's a great question. I think that in the future, when the computers have taken over, I think we will continue to value insight, and I mean that will always be the point of mathematics as far as we're concerned. I think that in some sense, like for example, with this proof with the Chebyshev recurrence relation that I was mentioning, I mean it's a very simple example, but I think it's an example where there is an insight to be gained, and that's that I'm not sure that a human really is getting so much from carrying out this. Oh, I'm sorry, I don't know what I just did. I'm not sure that a human is really gaining so much from carrying through this calculation here that I indicated. I think that possibly a human is actually gaining more insight from observing that, if you just write down, the recurrence relation and the inductive hypothesis in the right way, that it sort of all adds up correctly. So I think that you could argue that in some sense, certain insights are more crisply expressed when you have to write in this language. I guess I would say for myself that, any latent sort of Bourbaki tendency that I had has been exacerbated in the couple of years since I started working on formal proof, that it's so clearly always the right decision to write something in the more abstract way, and that it, in the sort of classic sort of Bourbaki advantage of abstracting away irrelevant details matters so much more when you're, working in a system where you have to verify every detail, that I do feel like you gain insights somehow when you're working in a system where every random detail you add forces you to fight. You do find yourself stripping things down to the bare essentials, and I would say that insight of abstraction is something that that you get. I feel like the proofs that I have written in Lean I understand on a far more abstract level than I ever previously did from, for example, teaching them to a class.
Okay, let me give you a hard time. It was exactly this slide that made me think of this question. I look at that lemma and I think, okay, you use this definition to prove it, and it wasn't a very nice proof. So then I look at the lemma and I think, hey, mn plus k goes to 2m plus k and k, so that's adding the two exponents and subtracting the two exponents, right? And I think, where have I seen that before? I know the sine formulas. Isn't that like cosine plus times cosine equals cosine plus cosine? And then I think, oh yeah, Chebyshev, that's cosine polynomials, isn't it? I think, oh yeah, that's a proof.
That's true. Although I have to say that I deliberately wrote this in such a way that you would not have to import the complex number library before establishing this fact about Chebyshev polynomials. I wrote this precisely because I was irked by the idea of importing trigonometry into a library about polynomials.
Now I'm trying to make the point I got insight by staring at that formula, thinking that proof is ugly. Why is it working? And I've come up with a proof that's going to be a one-line proof and transparent. So when is Lean going to help me do that?
That's true, actually. So I think somehow perhaps the point you're making is that there are relationships between fields of mathematics that you don't necessarily get when you have this rigidly enforced tree structure to mathematics, with each thing being, rigidly derived from a precise set of parents. That the cross-pollination among the leaves of the tree, to mix two biological metaphors, is not necessarily showing up in a world in which everything is the directed graph of theorems. On the other hand, one thing that I think that I believe more strongly now than I did 2 years ago is, I think 2 years ago I believed in the conventional sense that many important results, there's sort of no hope to make a universal library, because there are going to be multiple ways of proving it, each of which have their own advantages and disadvantages. I think I have increasingly come to believe that although that's the case in some situations, in many situations that's simply a sign that there's a better way which unites both of the two ways that you can describe. So I know this is a very grandiose claim that certainly is not true in all cases, but I think I've come to believe in more cases than I previously did that there are proofs in the book, one canonical right ways of doing things in many branches of mathematics where I wouldn't necessarily have thought it before.
Okay, well, thank you.
Okay, I see a question from Jack Levinson.
Hi, Heather. Thank you for the talk. Really enjoyed it. I'm curious about tactics. And so you had one in your demonstration with linear arithmetic, and you commented on the sort of limited scope of the sorts of proofs that the computer is able to search for. And to me, it seems like this would be one of the most interesting ways to make this system more useful. And then so I'm curious, how hard, can you comment on how hard it is to I guess you said diagram chasing, for instance, is hard to make precise, but yeah, so I'm curious about making new tactics.
So I think it's extremely important. I think there's an interesting question whether the AI is coming fast enough that somehow the AI will sort of invent its own tactics first for this kind of four-line argument, or whether we first come up with the precise set of instructions to carry out a certain kind of argument. I'm genuinely not sure. But I think, sort of as I was saying at the end of the talk, that there are many situations where what a human does to solve a particular kind of problem, is certainly a technique that can be learned. All humans do it the same way, and it's sort of, sort of repetitive in some sense. And I think we just have nowhere near enough people. We have now a fair few mathematicians who are users of Lean. I'm not sure what number would amount to, but perhaps we have 50 to 100 people who have a PhD who are regular users of Lean. But within that number, the number who are writing tactics is tiny. Perhaps it's 5 or 10. I wrote my first very baby tactics last year, a couple of years after first starting to experiment with these languages. It requires real computer science chops, and I think there are people who have those chops and could be doing this for us. But I think it's just surprisingly difficult, even for something that seems so simple, like combining a bunch of inequalities to get another inequality.
Thanks.
Okay, and there is another question from Franco Saliola.
Hi, Heather. Thank you very much for the talk. I really enjoyed it. My question kind of goes back to Peter Scholze's comment on whether you can actually read the output.
Yes.
So from the example that you presented at first in the demo, it kind of seems like, with a little bit of, care, one might be able to write a software that would take a Lean proof and output something that's more human readable.
Yes, I think that's definitely true. And I will mention the work of Patrick Masseau, who's a topologist in Orsay, who has been working on this kind of thing. He uses Lean in his undergraduate teaching, and he found that the students, in some cases, were able to learn to use Lean, but not able to sort of understand or describe in words the proofs they were coming up with. And he wrote the kind of thing that you were describing for precisely this reason. I think there are two separate problems. I think that writing something that takes our language and translates it into Lean instructions is obviously very hard, and going the other direction, going from the instructions to the description, the human readable description in sentences of what's happening, is easier. So I think that's certainly achievable. There's somehow the question of, well, I don't know, perhaps this is Stockholm system, but the question of how much it adds. But, I guess, I now read Lean better than French. And, it's, once you learn to read something, it doesn't cost you somehow too much an extra thought. But I think you're right that it would be a tool for popularization, for example, which would be very valuable.
Yeah, I was thinking more along the lines of popularization. I have a very similar experience as you. Like now, like I've learned Python quite a bit, and I use Sage a lot for my research. And a few times I've actually looked at the source code of Sage to look up certain formulas instead of actually going to the papers where they were first proved.
Yes.
Because it was much easier to read the Python because I understand that language and not, some mathematician's notation.
Yes. Yeah, but as I said, perhaps it's Stockholm syndrome.
And if I can ask another question, there are other proof systems. So what are one of the advantages of Lean over some of these other ones?
So Lean, I think, has the most active community of mathematicians for, really just sort of the reasons of, a small number of people becoming a larger number of people, becoming a larger number of people. One decision in Lean that I really value is the decision to maintain this single unified library. I think it's very natural to mathematicians to have a single unified library in which everything can reference everything else. And I mean, to cite, another very widely used and popular proof assistant, Isabelle, that I mentioned before, they have a slightly different sort of ownership model where the individual pieces of mathematics that are written are sort of maintained by the authors. And I think it makes it harder for them, if somebody is doing something about Banach spaces that just has one lemma about additive groups, sort of it makes it harder for that one lemma about additive groups to join the right place and therefore to be usable by other people who need that lemma about additive groups. So I think that this sort of design decision that is very natural to mathematicians is implemented, as far as I can tell, really only in the Lean library. And it takes work. I mean, I'm one of the 20-odd maintainers of the library who review the new contributions and make sure that the things go in the appropriate places. And it is a non-trivial energy that I really should be spending doing other things, but I think it's a worthwhile investment to have a coherent body of mathematics.
Thank you for those answers, and thank you again for the talk. I really enjoyed it.
Thank you.
Okay, I see more hands raised. So Kubra Aksoy, do you have a question? We cannot hear you.
Can you hear me?
A bit weak.
Okay. I want to ask about the proof in Lean. How to ensure the proof in Lean is soundness or consistency?
So this is something I don't know very much about. There's, as I said, an external sort of compiler that is taking each instruction you give, and if the instruction is not a well-formed statement, it will give you an error in the same way that if you write Python or whatever and you give Python a line that is not well-formed, the computer will give you a bug. So you write a series of instructions, and if they cause no errors, you hopefully reach the state at the end where all of the goals that you have been proved. But I agree that at this point you're now just outsourcing the work of checking it to this piece of software, which is doing the mathematical work of verifying that everything goes down to the axioms. I don't know very much about this. There are people who care a lot about this and who write checkers for these checkers and checkers for those checkers. But I know less about it myself. Okay,
thank you. And the following question is about the, it is Microsoft research projects. What do you think about why Microsoft interested in this kind of project?
So I know relatively little about the history sort of before my own involvement, but my understanding is that Leonardo de Moura, the person who wrote Lean, was an eminent computer scientist well before inventing this theorem-proving language, and he had a permanent research position at Microsoft Research, which he at which point he began to be inspired. So I mean, computer scientists are interested in this kind of software because in addition to using it to check mathematical proofs, you can use it to make theorems about other pieces of software. So say you have the operating system for a jet and you want to make sure that the jet is not going to collapse. You would like to write a specification for what the operating system of that jet is supposed to do, and then to formally prove, a very tedious theorem saying that in all possible cases, indeed the operating system of the jet is going to perform according to that specification. So this is, until, this is by far the largest part of the field of interactive theorem proving as far as computer scientists are concerned. And for them, the mathematics is just a hobby, but this has been the motivation for them to develop this kind of software.
Yeah, okay, thank you very much.
Okay, I see another question from Andrew.
Yeah, a couple of questions ago, you said you're the gatekeeper or one of the gatekeepers for introducing things into the library.
Yes, I'll mention that Frédéric Dupuis, who is also on the call at the University of Montreal, is another of these gatekeepers.
And you, in the last question, you talked about there's a way to verify coherence of logic in some of these programs by proof. I think it's check programs. But it still worries me that you've got programs that say they do one thing, but actually they do something subtly different. So have you got?
Yes. Yeah. Okay. So you're right, and I can give you an example from just a few days ago. So I encountered a problem in developing the theory of vector bundles in Lean that I could not prove something that I definitely expected to be true, and it turned out that in the definition of vector bundles, which a graduate student had added as a part of a project a couple of years ago, there was a subtle error. The definition of vector bundle was correct in finite dimension, but did not apply in the Banach. It was not correct in the Banach space setting, which I was trying to use it for. And so this is probably exactly the kind of thing that you're talking about, that a definition, somebody has made a modification of a definition which seems very plausible to them, seems like a reasonable adaptation or streamlining of the textbook definition, or even just the textbook definition is very subtly imprecise, and that when it's translated into Lean, that mistake carries over and then therefore does not say quite what you expect. So I don't know if this is what you're getting at, but I agree it's a concern. I think that the only way that you can fix this kind of empirically, if you prove some theorems about vector bundles, as I was doing, I think eventually you will discover the mistake, because you'll find yourself unable to prove the things that you thought that you should prove.
Yeah, this is exactly what, in fact, it's a brilliant example you just gave. No, I'm very interested in what value proof checkers or proof verifiers or proof helpers give to proof in mathematics, not as a computer scientist, as a mathematician, and I just feel like almost every problem that comes up in proof, when humans do them, there is an analogy in the Lean world.
Yes, I think that's true. I think that tendencies that we have in the human world are in many cases somehow, reflected and even sort of magnified in the formal version.
Thank you.
I don't see any more questions. So let's thank Ether again for a very nice talk. And yeah, thank you very much for introducing us to this world of automated proof.
Thank you. I hope to see many new users. You'll be welcomed.